All right. Hey, good afternoon. So how many of you guys came to the breakout session the last session around? Okay. So this stuff is new for the rest of you, yeah? Cool. So let me give you a little bit of an overview, then I'll dive into a little bit of a Visual Studio sort of session, and then show you how to get started with Visual Studio Code as well. And then those of you all on Mac will actually be able to get this thing running. There's a whole bunch of documentation material out there that you can follow. So I'll point you to some of it. We only have 20 minutes, so I'll take questions at the end, if that's okay. Is that right? Cool. So the Quantum Development Kit. How many people done anything with quantum computing so far? Right, handful of people. No heckling, right? So the quantum computer that we're talking about for the Quantum Development Kit is actually a simulator that runs on your local machine, okay? There's a cloud-based simulator, don't worry about it. Just worry about the one on your machine. You get that for free when you download the Quantum Development Kit. The way you program against the quantum simulator is actually quite interesting. It's not like programming against a normal set of libraries. It's really an adjunct coprocessor. So you think of the quantum simulator itself as a coprocessor, and you issue instructions to it. And the instructions that you issue are actually in the form of a Q-sharp program. So if you want to think about the big picture, basically you have a quantum computer in this case. When we get the real device, you'll have a quantum computer, some cryogenic control, and then you have applications and software. In the case of the simulator, what we have is just applications and software and the simulator underneath, right? So logically speaking, you write your program in the light white dot square. So you write your host program in whichever language you want. C# is a fine choice. So is F#, right? Or even Python. Then you can write the stuff that you want to be actually executed in terms of a quantum context. You write that in Q#. And you make use of the algorithm, the libraries that are available. And I'll show you how you can get access to those as well. And then against the classical runtime, you can actually run it against the local simulator, exactly as I mentioned to you. Now, how many people have actually downloaded the QDK so far? And how many people have actually figured out how to read Q#? Okay, so cool. Any questions on why we actually created a new language? Does anyone want to know? Cool. All right. So basically, when you want to program a coprocessor, even a traditional like graphics coprocessor, something like that, the traditional approach is to have a host language and just slap on a bunch of libraries which will make calls to the coprocessor, right? So when you want to do something complicated that the coprocessor is capable of doing, you'll end up having to write the sequence that's effectively a bunch of library calls that'll get intercepted and then shipped off to the coprocessor to run. The problem with quantum computing is that it's a domain in itself, and the domain is actually a fairly complex one. And if you want to write programs in that domain, it's good to have a type system for that domain. And what you don't want is, you don't want the type systems of the host language and the domain to actually conflict with each other. Similarly, we have the ability to reason about the program that you want to send across. So rather than intercept a bunch of library calls and then try to figure out what's going on, we are able to look at the whole program and do whole program optimization. So we can figure out what it is you're trying to actually run on the quantum computer and actually rewrite the program appropriately and optimize it out so that you can actually do a good job. And to be able to do that properly, you really need a different language. So the idea that you can reason over the program that you want to write basically means that the compiler gets into the mix and is able to do the optimization for you. And so this is why we picked a new language. So to develop a new language, that allows you to express only quantum computations and to express them correctly in its own domain. So the syntax that is fairly familiar, I mean, it's basically a C-style sort of brace-based syntax, but it's functionally inspired. So there's a lot of stuff in here that you'll get quite naturally if you've like programmed language like F#, for example, like immutability, the ability for not being able to mutate state, for example, is something that we turn out to be quite useful. So I'll dive into the demo at the moment, and we'll get an idea of what it is that we're doing. So let me see here. Now, can everybody see the code? Or do I want to zoom in further? Is it okay? All right. Now, actually speaking, people who came to the talk before will have seen this before. You have the host program is actually written in C# in this case. And what we're going to do is create a handle to a new quantum simulator. And this is, in fact, how you get a handle to the simulator object. And once you get the handle to the simulator object, you can then pass it to an operation which you define in your quantum code. You pass it the simulator, and you pass in whatever arguments you want, and the simulator will actually be used to run that quantum operation on it. Now, Q# has a whole bunch of constructs. So we have the ability for you to define functions, which are pure functions from a functional perspective. So functions that have no side effects, functions that cannot call quantum operations, for example. So things that have no side effects and are pure, you can define those. And then you have operations, which are effectively sequences of side effectful functions that change the quantum state of something. And so in this particular case, I've created an operation called teleport classical flag in Q#, and I've given it a body. And the body of the function is, when I step through it, will actually show that it will take the state of one qubit and transport it to another qubit. And because of the laws of quantum computing, where you can't clone arbitrary state, teleporting turns out to be somewhat useful. So I'm just going to take you through what it does here. Now, I'm not going to walk through the physics of what's actually going on, but the idea is that this is a development environment that you can get behind, and you can put breakpoints in your Q# code, for example, and notice that the value true was passed in from the program. Let me see. So the flag here is actually true, and I can continue. And I expect to come back with the flag being false, because in the program, the first instruction was send true and then send false. So if I just run this code, I'm able to see the output. Let me see. Oh, it's showed up on a different screen. So it shows that this thing runs. Now, why is this even interesting? I wouldn't write code like this classically, because if you think about what's going on over here, I've just created like comment blocks and say, this is what we want to do. But really, if you wanted to write it in a proper software engineering way, you would break it out into constituent functions and be able to modularize the thing and being able to do interesting things with it. So to refactor this code, let's say we dive in to this thing. We're still going to send true and false. Let me just close all these windows for a minute. But I want to rewrite the teleportation demo in such a way so as to teleport an arbitrary state. Wait, hang on. I'm so sorry. I'm still going to teleport true and false. But the first thing I'm going to do is I'm going to break out one of the pieces of the code and create its own operation. So to entangle two qubits together turns out to be quite a useful operation. And then you can introduce this concept of being able to say, here is how you create the inverse of the operation. And this is kind of why having a language is useful. Because if I didn't have this, to create the inverse of that sequence of operations, I would have had to manually keep track and write that inverse myself. And now you have a software engineering problem of having to maintain those two pieces. But because we have a compiler that can actually do the symbolic computation of it, every time we want to get the adjoint of the prepare entangle pair operation, the compiler can actually go to the body and say, hey, what is your sequence? And then compute the automatic adjoint sequence for you. And this kind of thing is really the power behind the language, the ability for you to do the symbolic computation inside the compiler itself. Similarly, I've actually split this out into the piece that prepares the state and the piece that actually does the teleportation. So now you see that the teleport message just takes two qubits, the source, the message qubit and the target, and then entangles the message with a given qubit and sends it across to the other side. So by just using standard software engineering techniques, we can actually create multiple methods, and we're able to say, okay, now I want to teleport a classical flag. What if I don't want to teleport a classical flag? What if I want to provide my own unitary matrix that prepares the state for me? So in this particular case, the only way to prepare the state of the qubit is in one state, or it's the zero state or the one state. So I can now use the same approach and create an arbitrary state. But to provide an arbitrary state preparation, I need to provide a unitary matrix. And a unitary matrix is something that has an adjoint. So how do I pass in a first-order function that takes something that affects a qubit and specify that it should have an adjoint? And this is kind of where the type system comes in, where when we say that the unitary that you pass in should have an adjoint, the language allows you to specify that. And now you're able to actually create an arbitrary state preparation and then call the adjoint of it over there. And by doing so, you can have proof that you've teleported the message across, right? So this should give you a sense of the kind of power behind the language, the ability to do standard things like encapsulation and so on, but also the type system that supports the ability for you to do higher order functions. So I'm passing in this particular case, I'm passing in an arbitrary unitary matrix. In this case, I'm passing in the Hadamard gate and saying, prepare my zero state in the Hadamard with the Hadamard gate and teleport that. So if I now run this 1,000 times, right, I expect to get about 500 times the state being prepared in the true state, and then the state being prepared in the false state. And because that's what the Hadamard gate will do. If I had a much more complicated unitary matrix, I could pass that in as well. And so you can see the sort of functional influence where you have a first order function being passed in as an argument to a function and then being sent across. I'm going to skip this one because this one actually talks about partial application, and you can actually use the prepare entangled pair as the thing that you pass in for the state preparation, because we only have another 5 minutes. So I'm going to step away from this at the moment and show you that this whole thing actually works in Visual Studio Code as well. So let me bring up Visual Studio Code, and you can see that it works in .NET Core, and we can run the same kind of thing where we were talking about before, where we build a bell pair and run it many times and so on and so forth. Again, the driver uses the same quantum simulator, and you can create your code in Q Sharp and run it in Visual Studio Code itself. So this approach basically allows us to run in .NET Core. So you can run it on Unix, you can run it on the Mac, and you can run it on Windows as well. So what else do I want to show you? Let me show you the libraries. So let me fire up. So if you go to microsoft.com/quantum, you can actually sign up for the kit, and you can download you can get started with the quantum development kit. And this will have links for the Mac, it'll have links for Linux, and it'll have links for Windows. And there's a whole bunch of instructions here about how to get started and so on. There's a reference for the Q Sharp programming language. And this is at docs.microsoft.com/quantum. And there's obviously the libraries themselves are fully documented out. You can also go to GitHub and see the Microsoft.com quantum libraries. This contains all of the algorithms that we ship with the quantum development kit. So you can start by writing code just the way I showed you, or you can actually use the libraries that are there to build more complex algorithms. So phase estimation and amplitude amplification, quantum Fourier transform, all the building blocks that you'll need for building real applications, or going through a course and writing up all the homework for it, for example. You can use the libraries to actually build stuff with. And I'll switch back to the PowerPoint and leave some links with you. And then I'll take some questions. So I think I'm done for this piece in terms of time. Happy to take any questions you have. I'm taking a question. So the question was, how do you debug quantum code? So that's a really interesting question. With a real quantum device, you can't actually go in and take a look at the state of things. So with the simulator, you can actually, if you want to, and it depends on the simulator. So certain simulators will give you full access to the waveform. Certain simulators will give you full access to all the information in there. But generally speaking, the way in which you write code uses asserts and uses like properties of the mathematics in order for you to figure out whether you're on the right track or not. Traditional debugging techniques are of limited value because all the computations that you do are actually probabilistic. So you may not get the same answer every time, and that might actually be perfectly okay. So you typically land up running the program doing kind of printfing your way out, but typically what you'll end up doing is you'll run through the program multiple times, collect the answers, and then kind of classify the results that you have to figure out whether you have the right answer or not. So the question is there something that helps you converge? So the language has certain constructs that allow you to specify bounded iteration. So you can say repeat until success, and if up until some condition happens, and there's a construct that allows you to do that in the language. But what that condition is up to you. And also, if you don't actually hit that condition, you'll notice that there'll be a failure, and then you'll have to work out what's going on. All right, thank you.